Hello everyone. Today we're going to have a problem in heat transfer by radiation. So this is a very standard and very informative example where we can actually figure out by following this with some assumption, we'll figure out what is the temperature at the surface of the sun. So what do we need? We need something from black body radiation. Okay, so if you haven't memorized, you need to memorize this Stefan-Boltzmann law, because otherwise a lot of problems will be out of your reach. So it talks about energy flux, where amount of energy, this is basically energy per unit time, per unit area. So I have some object, so this is its surface. That surface is at some temperature T. Then if I take a unit area, then amount that radiation, that's total amount that coming out, would be given by this right side thing. The epsilon equals to 1 for black body, and body is different than black, then you can be from between 0 and 1. So black body will absorb also with epsilon 1 and emit with epsilon 1. Sigma is a Stefan-Boltzmann constant. It's a universal constant. It doesn't depend on what type of body you have, whether this is a aluminum, copper, carbon, iron, whatever. Okay, so sigma is a universal constant, and T, the way this form is written, T is in Kelvin. Okay, so it's absolute scale of temperature. So if temperature is 0, then nothing will coming out. Okay, and this is we call it heat, but this is basically energy, energy that's coming out. So if this is, say, sun, then the surface of the sun, this energy is in, we might call it radiation energy, and so that's the same as delta Q. Okay, so this is like a loose term to call it heat, but it's just energy coming out in the form of radiation in this particular setting. Okay, so this is say this was sun, so this is the radius of the sun. So we're looking at what's coming out. This area will be 4 pi r squared. So this area is 4 pi radius of the sun squared. So if I knew how much energy was coming out of here per unit time, if I knew that, if I knew this numerator, then I would know the left side of this, right? So let's see, radius of the sun is given to us, so we know this. Then somehow the numerator I can get by knowing from the sun is coming out, and this earth is way out here, earth is here, and on that earth, how much is falling is given by this. So it is falling this amount of radiation energy per unit time, per unit. So if you took assume that the sun actually is given out in all the direction, then I think we can find the numerator here. Suppose we can find the numerator. Then on the right side, carrying on to the right side, we know that, so we can figure out this using this equation. All right, so our focus is to find the find this delta Q over delta T. So what's this delta Q over delta T over here? So that's, well, this Earth is, you can say, I can imagine a sphere, a spherical surface, and over here you have per unit area of this is, let's call this some x. So x is falling here, and this thing at a distance from the center is d, right? D is given, and I want to know what's the y over here. So if the flux here is x and the flux here is y, which is the left hand side, so we are given energy flux at x, left side of equation 1 of 1 is energy flux at y. Well, if the energy were going to go through this surface and then had to go through that surface, so all the energy that came out of here has to go through the entire surface, right? So let's call this flux phi at x, and let's call this phi at y. Basically, this is energy per unit time per unit area around x, and this is the energy per unit time per unit area around y. So I'm going to look at all the energy that's came out of here. So the energy, so this let's call it surface A, and let's call surface B. Energy through surface A per unit time. How much energy that comes out of there? That will be the flux at y, or the flux is here, times the area 4 pi. So that's how much energy must have come out, because this is per unit area multiplied by the area of this surface. And then surface B per unit time will be phi at B, phi at x, we're calling x, point x, times 4 pi distance between Earth and Sun square. Okay, so this, we have been given phi y. So phi y is known. So these two energy must be equal, because whatever energy came out of here must also come out of here. That make it phi y. Let's call it phi x. Phi at this point we're calling x at the surface of the sun, times 4 pi rs square is this is, make sure I'm doing it right. So this was called x and this point was called y. So this is y. So phi x is at the Earth times 4 pi d square. So this is what we want. That's the left side of equation 1. So I can solve this, and so phi y is equal to d over rs square phi at x. Okay, so that must equal to sigma epsilon t to the power 4. Okay, let me clean this up so I'll get to the new slide. Okay, so we have the flux, which stands for this. We have that. So d over rs square phi x is epsilon sigma t to the power 4. So I can kind of so this is the flux x, we're calling it. This is equal to flux of x, flux at x. So solving for t to the power 4, this t would be everything to the power 1/4, and we'll have 1 over epsilon sigma d over rs square phi x. Now we just put in numbers, right? So numbers will be 1 over 1 times sigma 5.67 times 10 to the power minus 8. And these guys are, d is 1.496 times 10 to the power 11. And this is 6.957 times 10 to the power 8. And that's a square. And phi x is 1361. This whole thing 1/4. Okay, so I put in the calculator, and I think I get 5772. So this is equal to 5772 Kelvin. Okay, now this is really a very standard kind of example, and you would get a variations of these kinds of examples from all kinds of places. First, after you've done with this, you can say, okay, suppose so here is an extension that you might say. Suppose I give you that, okay, Earth is a black body. So amount which it is, we can assume, just for the sake of argument, amount of radiation comes in is amount of radiation emits. Okay, so can we assign the surface of the Earth some temperature Te? Can we use this to find answer this? So there's one extension you can try. Another extension is, suppose I give you the distance to Mars, Sun to Mars. Knowing all of this that we just figured out, can we figure out temperature? And so number 1 I give you, number 2 I give you is assume Mars as a black body. Can you give me temperature of Mars surface? See what you get, and see if those numbers make sense to you. Those are some of the things you might want to try. Don't forget to subscribe, and if you like this kind of conversations, definitely hit a like button. You can leave comments, and you can ask me if you want me to solve some new problems. I'll go take a look at it and try to respond. Okay, thank you. Bye-bye.